So as we consume acid in natural systems, we can draw carbon dioxide gas into solution, meaning into either water or, in my first example, into blood. So in some natural systems, and I'll give three of them, what consumes the acid so that we can get carbon dioxide into solution? Human respiration is actually a cycle. In cells, hemoglobin comes to the cell and exchanges oxygen to the cell in exchange for metabolic acid H+. And the metabolic CO2 from the cell goes into the blood then as bicarbonate. When it reaches the lungs, then the bicarbonate neutralizes the acid into CO2, which is running this reaction this way. And the CO2 goes into the air as you exhale. And this enables hemoglobin then to reuptake oxygen and goes back to the cell. So this is a cyclic example. Chemical weathering in rocks also consume acid, and also release base. So carbonate rocks really don't do much for us. There are deposits of these calcium carbonate rocks. I showed you the ones of the stromatolites. If you dissolve those with acid, you release CO2. We don't want to be doing that. In fact, limestone carbonates like that are used in the manufacture of cement. So actually one of the biggest emitters of CO2 in industry is actually cement manufacturing, because as you're using calcium carbonate, you're driving off CO2 to make calcium oxide, which is lime, the principal ingredient in Portland cement. And so you're driving off CO2. But there are other rocks, primarily silicate rocks, feldspars, which are common minerals in granites, and they decay away to clays, as shown by the reaction on the bottom. And in the process, acid is consumed. You can see that the four acids were eaten up here and locked up into this clay mineral over here with a little bit of quartz left over, and it releases some potassium salt into the water. So this is actually the origin of salt that ends up in the ocean, but in the process it removes acid from solution, and in concert with CO2 it enables bicarbonate to go into groundwaters and river waters. In the ocean, and it's probably the biggest uptake of CO2 is in the ocean through photosynthesis. Photosynthesis uptakes the acid as well. So you can define photosynthesis of the phytoplankton in the ocean as a chemical reaction with set ratios. These are called the Redfield Ratios. So in photosynthesis, it's very common to have 106 carbon atoms consumed along with 16 nitrogen atoms consumed with one phosphorus atom, and also 18 hydrogen atoms as acid. So here's the reaction down here. 106, 16 phosphorus atom there, water and acid going to algal carbohydrate and oxygen. So this is the photosynthesis that's uptaking the CO2, and it's doing that by consuming acid here. If we continue to stabilize more and more carbonate in solution by consuming more and more acid, driving the pH to the right here, driving it to higher numbers by using up the acid rather, we increase the alkalinity, which is the amount of total carbon. Carbon, as alkalinity goes up, which is the ability of the solution to neutralize acid, goes up, it draws in the carbon in the form of CO2, gets dissolved in the water and goes into the various components like carbonate and bicarbonate. So the red line shows the increase of the inorganic carbon that we've been able to take from CO2 gas in the air and put into solution as the alkalinity increases, as we increase the pH. So we've got a bunch of carbon in solution. What does that do for us? Eventually, it builds up to a level. These are in green is the stability area, where if you have these combinations of pH and carbon, you produce a solid. And in this case, the solid is calcite. It's the fundamental mineral solid of the limestones that you saw the stromatolite fossils in. So when you crank up the carbon dioxide in solution in the form of bicarbonate and carbonate, eventually you're going to produce a solid phase calcium carbonate, and this precipitates on the ocean floor. So this is the Earth's natural method for depositing, basically taking carbon dioxide out of the atmosphere and putting it on the ocean floor. And I mentioned that photosynthesis is a part of that. Even though CO2 going into the ocean increases the salinity of the ocean, which is dropping pH, and that's a real problem, you can counter that by fertilizing the ocean, which does two things. It consumes the acid as well as locks up the CO2 and bicarbonate in the solution, which can then deposit the solid carbonate on the ocean floor. So one proposal for geoengineering, if you will, taking carbon dioxide out of the Earth's atmosphere, is to fertilize the oceans and deposit calcium carbonate on the ocean floor. I mentioned in the past the atmosphere was 100 times higher. That just shifts things around a little bit. So we have maybe a little higher concentrations over here. They shifted to lower pHs, but in general the same thing. The alkalinity goes up. The amount of carbon from the atmosphere goes into the solution, and we lock it up with CO3, the solid calcite. So this is how the Earth got rid of the early CO2 levels. They were 100 times higher than they are today. That results then in the natural carbonate formation that I showed you before. Deposits of limestone around the world are deposits of carbon from the ancient atmosphere laid down on the ocean floor. And so we ask, can we mimic this industrially? And the answer is yes, and this is the key to the process that I'm going to describe. And the technique that we use to start this process is brine electrolysis. We start with brine electrolysis, we produce a base, and then we aerate the base solution with carbon dioxide, which forms carbonate mineral.